Am I audible? Sorry, can everybody just get seated, please? So we are starting. There are seats up front as well, so please come up closer. All right, so let's get started. Good evening and welcome everyone. Welcome to Fabric. Today we are going to talk about engineering agentic AI systems. I'm Abhijit Kesarkar. I'm the head of technology at Fabric, and I have with me Anuj Pundlik. Both of us will be talking about agentic AI system today. Just a few housekeeping announcements before we start. We have two emergency exits, one on that side and one near the lifts outside. The bathrooms are outside, and we have drinks and water in the pantry behind you. A quick word about Fabric itself. So Fabric essentially is a group of passionate technology professionals who build bespoke software solutions for our clients. So we have expertise in design thinking, strategy, software engineering, and we love to solve complex business problems for our clients. So that's what we do. Today we'll be talking about AI agents in general and specifically drill down into some of the insights around how are we going to be building AI agents or agentic AI systems. What are the challenges? What are the things you should consider when you're going to be building solutions for production? So I think you would have heard AI agents almost everywhere, right? So you see it everywhere, and I was scrolling on my Facebook, and I got a message saying that, hey, a 10-year-old is building AI agents. If you're not doing that, you're missing out. So it's literally like, it's just everywhere. But a lot of times, a lot of these AI agent systems that let you build AI agents, we start with, starting with some sort of a POCs, but now what we're going to talk today is mostly about really when you want to, go to production, what are the things that you will need to consider, which, it's easy to just get started over a weekend and build something out. But if you really want to build solutions for your customers, for their clients, there are a lot of other considerations that you'll have to do, and that is what we'll be focusing tonight. Yep, so we already introduced. So the agenda is roughly going to be, we're going to start with some basics so that everybody's on the same page with what basically AI agents are. Then we'll look at a use case that we have built internally, through which there are a lot of learnings that we went through while we built that use case out. So we'll categorize our learnings coming from that, and that's basically the whole exercise today. So as I mentioned earlier, you open any website on internet, you will see AI agent on the center of the homepage almost everywhere, right? Somebody just mentioned a few minutes back, like some companies just posted that they're getting into AI and their stock skyrocketed. So there's a huge amount of hype around AI agents, AI in general and AI agents in particular. So we just want to, along with the hype, there is a lot of agent washing as well, like a lot of products, a lot of software. Even if you're just doing basic automation, they tend to just term it as AI agents working for you. So we'll try to understand what do you really mean when we say when we talk about AI agents, and then we'll see what are the main considerations when we want to design a system using AI agents. So as I said, let's start with very basic, and I think the basic is LLM, yes, because the LLMs are mostly driving the whole AI revolution that we are seeing everywhere. We take a very basic example. What LLMs do is that they are very brilliant in understanding the context of the user. So essentially, a user is asking a question. There is some sort of a input going to LLM, and it is giving you back a response. It's basically a model, simple input and sample output. But the brilliance lies in understanding, reasoning, what is the input, and giving really like intelligent answers to it. So that is essentially what LLMs are. They have exceptional reasoning capabilities. They have exceptional understanding of what user is asking, and basically return something. So, when you're providing all the information to it, it can understand that information, and it can respond with a very detailed output that you would really find interesting. And that's where the whole hype started, when you started seeing fantastic outputs like AI generating a lot of fantastic content, whether it is photos, whether there are images, videos, text, understanding, comprehending. So that's where the whole hype started. But we all know that the models themselves there are certain intrinsic limitations around that. They are trained on a certain amount of data. So the large language, there's large amount of data that they're trained on. That data also is sort of a limitation for them. So anything that is beyond that data, which probably is your proprietary data, is something that they would not understand. They would not understand beyond certain amount of time, after which they don't have data of. So understanding real-time events, something that they cannot really understand. They're hard to adapt, in the sense that making them understand your own proprietary data is essentially tuning them with more data, and it's a hard process to achieve. It can be done, but it is still like it's not as easy as just asking some questions around it. And it's also very passive in nature. So all it does is, and it will never fail to do, is respond to you. So whatever you ask, it will make sure it will respond to you with something, some answer. And those answers sometimes can, as we all know, have hallucinations, certain incorrections that may cost you if you're not really looking for them. So if you take a simple example like, hey, this is a conversation or an article, can you please summarize for it? You're passing all the information to the model, and the model is making a judgment based on what information it has been passed, and it will return you a proper summary of that. But let's say when you ask the model, hey, what is the temperature of Melbourne tonight? It will not answer that, because it is probably rooted on data until a certain point in time. Now, don't mistake it with the way we are using ChatGPT these days. It will now answer, but those systems have evolved, so they are not just basic LLMs. We'll talk about it a bit later on. But that's essentially are those limitations. So this is just a hypothetical WhatsApp chat between a user and an LLM. So yeah, as I mentioned, if you ask them to summarize, it will do it. But if you ask what is a recent thing like a temperature in Melbourne, it can't answer. Do you have information on our learning and development budget? It can't answer, because it's a proprietary information. So even though LLMs are fantastic, these limitations is what actually driving all the innovation in AI. So what we are seeing recently or in the past, all the enhancements, all the developments are around compound AI systems that make use of LLMs to help us or address us better. So essentially, we already know that, so LLMs themselves have evolved over the last 2-3 years. It's not that LLMs haven't changed. LLMs now can handle a lot bigger context. They are actually getting better at reasoning, so they are actually getting exceptional at reasoning. They are becoming multimodal, so they are able to understand multiple modes of inputs, whether it is text, images, audio, video, all of that. But still those initial constraints, they remain. So the rest of the evolution is, when we want to really solve more complex problems, is we have to design solutions such that it can make use of the brains of LLM and still be able to get the desired outcome that we want. So these are what I would call as compound AI systems. So you would have heard terminologies like RAG, retrieval augmented generation. So it's basically an architecture that if you want to work with proprietary data with LLMs, the model doesn't know about your data. So RAG is just another way of finding the data first. So for example, I have a bunch of policies, and I have a very specific question about one of those policies. So you would essentially first find, based on the request, what is the policy, and then you take that policy information and give it to the model, which then now has all the information that it needs to answer the question. It's all part of the context. So that's how things work. That's how you could make better use of LLM, by building better software systems around it. And this is the trend that we are seeing. The evolution is around building more and more elaborate software systems around it that works around the limitations of LLM, that help us solve the complex problems. So we've seen the need for accessing real-time information. So there came the capabilities of something we call as tool calling, where the software systems can start using tools, which maybe you can think of APIs as an example of a tool. So use the LLM as a brain and then use APIs to feed or get real-time information about system, and then again work with the LLM to solve more complex problems. So we've seen evolution around this. We started getting tool calling, then we have MCP and AI agents essentially is the next evolution of that. So when we say AI agent, basically it is nothing but a software. Yeah. So it may sound like it's another AI model or something like that, but it is essentially a software built around an LLM, which has certain capabilities that help it decompose a more complex problem into something that you can use LLM to solve. So what it essentially does is, it has a reason, act, observe, and repeat loop. So whenever a user gives or asks a question, AI agent essentially is going to ask LLM, how do you solve this question? The LLM is the brain. It will reply with the steps that it needs to take. Now, AI agent, to be able to really effectively work, also needs tools. So tools, as we saw earlier, is nothing but a set of APIs, systems that can be accessed through software again. So then AI agent can then make use of those tools. Again, go back to the LLM saying that, hey, is my problem solved? And the LLM will be mostly acting as the brain to say yes, it is solved, or no, If no, it will keep on iterating until you get a valuable response. So that's the loop that a agent runs through. If you take the same example, let's say the user wants to know what is the temperature in Melbourne. The AI agent will ask the question to the LLM model. Hey, the user wants to know what is the temperature in Melbourne right now, and we have an API called get temperature that we can use. What should I do? So the agent is just asking a simple question. Now these are not the exact semantics, but this is essentially what the sort of conversation going on between the agent and the LLM. Now LLM here is just basically using its reasoning capabilities to say that you need to know what is the temperature and you have the API. So logically you should be calling that API with this input. So AI agent is just returning, the LLM is just returning what the next step should be for the agent. The agent calls that API and it gets a, let's say, 500 internal server error. Agent doesn't have the brain to understand what happens. It goes to LLM, says, hey, it gives the whole context again, because LLMs are sort of, they don't know, they just need everything fed to them. So it says, hey, user wants to know what is the temperature. Here is the API we have. I called the API and I got this error. What should I do? Now the LLM is having all the information in that context that it can say, hey, that's a retry error, you should probably retry again. Again, then the agent is now observing that and taking action based on that. So it probably triggers the tool again. It gets some response. Let's say the temperature is 20 but feels like -4. It goes back to the LLM again and asks the same question. This is what the API returned. What should I do next? The LLM response tell the user it is currently, so it gives the exact response that the user needs to see. So what is happening here is the agent is essentially acting as an orchestrator more than anything else. It is dumb, but it is making use of LLM's capabilities to solve that problem. So a problem that probably what LLM couldn't have solved on its own, the agent is just using LLM as a brain. If you look at what the LLM is doing, it is getting all the information as part of the context, and it is just making a logical reasoning based on that and returning what the agent should be doing next. And this whole thing ends up solving a problem that otherwise wouldn't have been possible straight away. So feel free to ask questions at any point in time. But this is essentially what LLMs are. Now this is what AI agents are. What we'll do next is just have a grasp of the landscape, because there's so many tools, there are so many frameworks, there's just so much happening. So it's very easy to get lost around this. So let's get some landscape overview of what things do we see around you. So if you are into software development, you would have heard about Claude. You would have heard about something like a cursor and anti-gravity. So these are what they would call as either agent-based software development frameworks. So two of them are basically IDEs that developers use, but they are rooted in AI agents. So essentially, this is again a software built using AI agents that solve for the domain called software development. So they are agents which are specialized in building software. So they understand what are the questions I should be asking to LLM, how do I break a problem into multiple steps, and how do I act upon it. So it has all the capabilities as tools, like editing the file is a tool, saving the file, committing file. These are all tools. It's a big topic altogether when we talk about tools and MCP, etc., where there is a lot of effort to standardize how you call tools, how you access tools, so that you can plug and play tools with different models. So this, in this example, what we are looking at is essentially AI agents who are working on the software development domain. We know about ChatGPT, we know about Gemini. We use them. We like even Perplexity and all other frontier brains that we use for a lot of research. They are also running AI agents. So even though it's just a simple chat interface, you can see that a lot of information that you're getting is synthesized by the agent. So it's not just calling a LLM and getting a response back, but it is also making sure that the response makes sense. So it has now abilities of accessing the internet to get the information and all of that. So the simple chat interfaces that we started with are now all agent systems which use AI agents to function. And so on. To be honest, almost every SaaS product would be a sort of a AI agent, because everybody wants to be in the game, and everybody is offering competition. So you will see whether it is let's say CRM tools, so they would have AI agents. So those are very domain specific agents that solve domain specific problems. So as you can see that agents can run very broad, or they can run very domain specific as well. So what we're going to talk today about, if you really want to build your own AI agent to solve a business problem. So something that for your customers, if they want to use AI agents to, let's say, automate some of their business workflows, how do you go about it? So again, now we're talking about a domain which is specific to your customer, to your client, that you can use AI agents to do the same magic that we are seeing across other products and tools. So to do that, you do need, as I said, AI agents are nothing but software, right? Like it's just another piece of code at the end. But to build your own custom AI agents, you have a lot of options as well again. But there are mostly agentic frameworks that, if you really want to build your own agents and deploy onto prod, you would be wanting to build on. There are popular ones like LangChain and LangGraph, which is essentially, it gives you a lot of, so you're literally writing code as your AI agents. So it gives you a lot of control. But there are also other frameworks which gives you a variety of abstractions and variety of control that you can use to build your agent workflows. So when you're going to start with it, you will have to pick one based on multiple factors, depending on what sort of, for example, if you look at a Google ADK, then it will be baked into a lot of Google GCP platform, and it will have a very opinionated way of how to build your agents. Most of these agentic frameworks will have that opinionated way of building your agents. So that would be basically a way for you to start building your agents. We'll see in detail what it really takes to build one, because when you actually start thinking about a use case, that is when you start thinking about the challenges that you'll have. So a lot of these frameworks give you those capabilities out of the box that help you get over those challenges. There are also a lot of low-code ones as well. Like, if you want to build an AI agent on a weekend, you can do those as well. There is Init and Zapier, so there are lots of options. I think quickly touching upon the use cases, I think this is one of the areas where a lot of people struggle understanding what it is a really good use case for building an AI agent versus what might be an over engineering. So agents typically, as you see, when there is when the inputs are the inputs are a variety of them, and you need judgment. They're not very deterministic. That is where they really shine. So if you have a very well-defined business logic, a very well-defined business algorithm, then using an AI agent can be an overkill. But wherever there are multi-step processes and you require like gathering information from multiple places and making a judgment call, those are the areas where it will shine. Especially when you have cases where the exception scenarios are just too many. So those are the areas where agents will shine, when you need to have a very resilient system where things can change and you need to make judgment based on what to do next. Those are the areas. So you have a couple of examples. Let's say a triage support ticket. Somebody raises a ticket and you want to triage that. It is based on what is in the ticket, so that can vary. Like anybody can type in anything, and you need to understand, if you really want to triage it well, you need to understand a lot of context. So it requires a lot of judgment to assess the severity and to really triage it properly. Whereas if you have an example where you want to extract something from a structured form and then you want to route to a team, that might look like something that agent can do very easily, but it is something that is very well defined. You can define those rules very well, and agents can be overkill, because you need to understand, when agents are running, they are incurring costs. So every step they take, whenever they're talking to an LLM, they are doing a lot of to and fro. They are sharing a lot of context, and that is a costly affair. So you need to make that call of really like how much of a judgment is needed, and what something, if you can just build using software, which itself you can build using agents though, but at runtime it is not going to incur you cost, is something that you can really think about. And finally, I think one important factor is, whenever you're building these, you do need a human in the loop. So the accountability, like even if a AI agent is taking a lot of decisions, somewhere having a human in the loop is very critical, because finally a human needs to be accountable for the decisions that are being taken by the AI agent. So you need to understand in the process what are the steps which are critical, where you do need a human intervention, so that you can catch a wrong decision if there is one. And because if like it is not caught, there can be a severe damage. You will need to make that judgment as well, how much of the damage you can take. Like some cases it might be fine, but in certain cases the severity could be high and you don't want that. So that being said, I'll hand it over to Anuj to talk about some insights around building. So going deeper into how you actually build one, and what are the concerns that should be taken care of. Thank you.
Okay. Thanks, Abhijit. So yeah, I think what I'll be talking about is the system that we built, the problem that we solved using that system. And the entire talk will be based out of what system that we are going to define here, and what were the learnings that we understood from that when we were building that system. So let me start with the system that we built. We decided to build an interview scheduler. The reason for this was not that scheduling interviews is quite a difficult job. It's not a difficult job to just go and search somebody's calendar. The problem with us is that we are a tech consultancy firm, and mostly we spend our time at clients, and where we don't really have access to the client calendar. So we are managing multiple calendars. So it ends up becoming a difficult problem for the recruiters to schedule interviews, where they have to go and understand from the other interviewers what their availability is like, get to a negotiating slot understand what that slot looks like, and then coordinate that slots with the candidate. So we decided to solve this problem where we would take in one message from the recruiter, which is basically saying that, can you schedule an interview for 2 people, let's say next week between 12 and 5 and anything but Thursdays. And I would like you to find 2 slots so that we can just take these slots and go and reach out to the candidates. And we would like to space these slots over the week as well. So in this case, the AI agent would basically, the entire agentic system would take in the message, understand what's the info related for that, what's required to schedule an interview, and then basically go and reach out to other people and get responses from them for what their availability looks like. And then once they have that availability, just go ahead and schedule an interview with them. So the way we build this is that we have a recruiter come in, where we send a Slack message. The Slack message would be just to schedule an interview. There would be a request parser, which would basically extract the intent from that message, understand if it is still an interview scheduling problem that we are solving, extract all of the relevant details from it. Once it extracts all of these details from it, it will go and say that, okay, is the information complete really? Then once it finds that, okay, if there's no information there's some information that is still needed, then it would go and ask the recruiter back again, hey, I need this information from you. Let's say, when you say next week, what do you want the days to be? When you say morning, what does the time look like? So all of these questions that will go and ask the recruiter back again. Once it finds all of this information available, it will go and check the availability with the interviewers. In this case, the interviewers may accept decline slots at their own time. This is completely asynchronous as a process, where they would say that they would take either hours to reply back, they would either take days to reply back, somebody's off on a vacation. And so collecting availability is completely asynchronous. Once they are to accept that availability, the system would then evaluate, is the consensus reached for that interview or not. So if that consensus is not reached, again, go out and reach out to people, try and negotiate a slot, and then come back and say that, okay, I have consensus now, and then go and schedule an interview. Now, the reason we thought that this is a very simple problem to solve as a scheduling. Turns out it's not. The biggest learning that we found out of this was, how do you really structure these agents? So let's understand what really an agent is made of. So every agent is basically the same 5 things. We have the model, which is the brain, which does the reasoning for whatever input that you pass it. It takes in messages and produces a decision. Fairly simple, nothing more than that. The way a model produces the output for a given input is based on a system prompt. Now, these are the instructions that you say that, okay, what it needs to know, what it needs to act on, how does it need to act on those things, and what's it really allowed to do. So all of these instructions are basically bundled as part of the system prompt. Now, the way it does perform these actions is basically tools. The tools are the hands for this AI agent, where it will say that, okay, how do I, as an AI agent, how do I act on this problem? What kind of API call do I need to do? What do I need to do in case of failures? All of these are basically what tools look for. In the case of, let's say, the interview scheduling problem, the tool could be just to send a Slack message. It could be to understand if if a slot exists which is overlapping with the other interviewer. So this way, these are the basically tools that we would pass in the system prompt for the AI agent to act on these and produce an output. Now, once it knows that it has acted on these tools, it needs to remember that it has acted on these tools, so that whenever you try to rerun the same problem, it does not start from scratch, but it knows what it has done so far. That's where memory comes in. That's where the state comes in, that, okay, if there are multiple AI agents operating on the same task, it needs to know what all has been done so far and what all can it do next. So that's where memory and state comes in. In the case of interview scheduler, it may be that when a recruiter sends in information to say that, okay, I want you to schedule an interview for this duration for these many people. Now, even though it may not have the entire information about it, it knows that, okay, I have extracted the interviewer name. It knows that I have extracted the candidate name. So this is where it stores this information in the memory. And then it picks up whenever, if the recruiter then says that, okay, I want you to schedule for next Friday, it knows what it has already extracted, and then it can start from there. Now, control logic is basically what governs all of this AI agent to do. When does it really need to stop? Now, in most cases, you let your AI agent run until it achieves its goal. The time when you basically pull the plug is when your budget runs off. That's the reality. If you don't code in the control logic, you're going to end up paying a lot of costs, and the cost could be in terms of correctness, the cost could be in terms of a lot of things. So control logic is basically what the Agile agent should not do, and how do you make it do a certain set of actions. In the case of the interview scheduler, it may be that, okay, now since I want to schedule an interview for 3 people and 2 of them have declined, there's no point in going ahead and trying to meet the goal of scheduling an interview for that candidate. It needs to break out. So that's where the control logic comes into play. Now, the first thing that we realized is that when we decided to build these AI agents, that persistence is not really an optional feature that you want for an AI agent. The way we discovered this was that not all memory is really equal. If you put the wrong data in the wrong layer, you'll pay for it. You'll pay for it in terms of tokens, you pay for it in terms of reliability, you'll pay for it in terms of correctness. Now, let's talk about the different layers of memories that we uncovered when we were building all of these AI agents. The first one is context window. So context window is basically what the model sees right now. It is finite and it is temporary and it costs you tokens. The more amount of information that you dump inside of the context window, the more amount of costs you're going to pay. It may or may not hallucinate in that context. The workflow state is basically what achieves the end goal of the system. This is a mutable object which all of the AI agent or multiple AI agents are operating on, and it lives in the run. It keeps on updating, keeps on changing as you go in the process. Then there's long-term memory. Long-term memory is basically, let's say that, okay, you scheduled an interview, it's in negotiation states. Now, the recruiter does not really have any idea into where the interview is lying with. So it needs to know, let's say the recruiter goes and asks the same system again that, okay, where are we with the interview? It needs to know that because from whatever it has passed so far, it will take that memory reference and then basically reply back to the recruiter saying, okay, that this is where the interview is with that. Now, the other layer of memory is basically the external source of truth, which this is the memory that you don't really control, but this is a very powerful memory that we forget that exists for us. For example, when you send the Slack message lives in another system. You don't really need to store it. This is where the systems and the APIs that you'll query to get that data out and then perform operations based on that. This is basically something that is not owned by the agent, but is maintained by the agent and is acted upon the agent and stored in a different software or different place which is outside of our agent. Now, when we realize that, okay, when we are building all of these memory applications, our agents are not supposed to be built to restart, but these are agents to be built to resume. For instance, if you're not doing checkpointing in your application, let's say you started a task where you extracted information, and let's say a tool call, which is basically trying to extract information about the candidate failed. Now, in this case, if you were to run the same problem again, you are no longer going to start from where you left off. You're going to start from scratch. This is incurring again the same amount of cost. This is again, the AI agent may produce a completely different output. So because there's no state saved, it does not really know what to do, and it will start from scratch and again will try to achieve the same goal which is you have given as part of the system prompt. Now, the way you tackle this is basically checkpoint every action that you do as part of your AI agentic workflow system. For example, let's say you started with task 1, you get to the end of the task 1, you checkpoint the state of that task, then you move to the task 2, checkpoint the state. So even if it were to fail at state 3, you would basically resume from step 3 again. You're not resuming from step 1 again. In the case of, if I were to draw a parallel to the coding systems which most of us have been using for Claude or anti-gravity, for instance, let's say that you're writing a function for computing something. Let's say that the AI agent wrote that function and then it were to use that function as a function, and you were to call that function in some other function. Let's say it failed to produce that output for how do you call that function. In this case, again, it would try to write the same function unless and until you checkpoint this. Most of the coding agents tackle this problem by implementing checklists. When you're using Claude, you may have seen that, okay, the implementation Plan generally consists of what items do I need to take as part of checklist, how do I need to act on these items, and then once I have these items finished, then tick them off and then move to the next item. Unless and until you have checkpointing available as part of your AI agents, there is no way that you can do human in the loop. For example, let's say that you started with a problem and you, in this case, when you were building the interview scheduler, our system went ahead and checked availability with candidates. Now, unless and until the candidates have replied, the system cannot keep on running forever. It needs to just hold itself, it needs to interrupt its state, and then it needs to resume from the same state where it left before, and then go ahead and make the remaining workflow act. So without checkpointing, there is no way that you can achieve human in the loop. Now, the same pattern when you're building AI agents, it holds everywhere, be it coding agents, be it your agents that you're designing to build PPTs, be it your agents that you're designing to gather information about something, research, and then send you a mail. All of these agents, they rely on the same concepts where you're balancing all of the 5 elements that I previously spoke about. If you are not balancing the memory aspect of it, you are going to start from scratch. You are going to end up costing tokens. In the case of coding agents, the memory in the case of coding agents is the file system. In the case of interview scheduler, the memory in the case of interview scheduler was the checkpointing state where we stored the output of what the agent acted on in the database. So that the next agent, when it comes in, it will pick from there and then resume from there. So the same pattern holds across all of the agents that you have been seeing across. It's just that how well are they organizing those 5 concepts, and that's what determines how complex your agent is becoming and how efficiently is it solving your problem. And so once we understood that, okay, how do we make an AI agent be checkpointing itself? Now that we know that, okay, you need to checkpoint, how do you do human in the loops? How do you, what persistence is not really an optional feature. Then we came to the point that who decides what happens in the workflow? So how much should the model really decide where you're going, what you're going towards? So at one end, there's deterministic workflows where you say that, okay, you have implemented everything that you have. Your code has these many branches. These are if else statements. Your code will run from one step to the other. And on the other end is an autonomous AI agent where you are making the agent decide what it does next. Now, in the case, if you have not defined the goal really well, if you have not defined how it checkpoints itself, if you have not defined the correct tool calls it needs to achieve to reach that goal, it will just go on endless and you'll never be able to pull the plug out. So most production systems really sit somewhere in between where you're not saying that you're not making the AI agent be deterministic. There's no way that you can do that. But how do you build the control system around it? How do you make sure that the path that the AI agent takes to achieve its goal, how can you make the path deterministic enough so that you are able to achieve the goal of the system? So it's not about, you cannot really control how an agent reaches its goal, but what you can definitely control is what happens after that agent goal is reached and how does my workflow progress ahead. So most of the production systems that you would build will generally live between the spectrum, mostly towards determinism, mostly towards autonomous end, with a hint of determinism that you would put in by putting some amount of control logic around it. So when you're putting this brings me to the next point, which is AI isn't really the default for everything. If you know the output of what 2 plus 3 is, don't really make an AI do it. Not every step really needs a model. Some of the steps are pure logic. Some of the steps can be computed. For instance, when you are building the solution, we initially, like everybody would do, we put a lot of all of our logic for evaluating consensus as part of a system prompt, where you would fetch data from what the user has been sent as their availabilities, create an output, and let the AI model decide what the overlapping window really is. Now, it did give us an output, but it costed us a lot of tokens. It may certain times not be able to determine if the output is right depending on the model that you would use. It may call the wrong tool in the first place, and it will end up into calling multiple tool calls across to get the end result. This way, you will end up compounding the cost that you have for building the agentic workflow. Remember, the cost, the only way you can control all of the cost and whatever gets outputted as a system goal is by building the control logic around an AI agent. And this is one of the reasons where you determine that not every step really needs a model. Some of the steps you can be done in a deterministic way, and some of the steps you really need a reasoning agent to do. So how do you really decide on how agents are really born? We started with the same example where we said, okay, we'll build one single agent which will do parsing, availability, consensus, confirmation. Now that's what basically our starting point was with. Then one agent was doing multiple problems. It was outputting to the same memory. It was trying to call multiple tools, and it was trying to reach the same goal, which is interview scheduling. Now, this ended up making the AI agent hallucinate quite a lot. Now, from this point, we realized that okay, the AI agents that you're building as part of agentic workflows, they need to be naturally split. The way you decide what an agent should be should reveal itself rather than you saying that okay, this is a logical capability, this needs to be an AI agent. Don't try to do that. Let the AI agent reveal its right size where it needs to know that okay, I need to access and store this information as part of memory. This is what are the tools that I can be aware of, and this is how my system prompt looks like. So reusability emerged in our case where we realized that okay, the request parser and the availability coordination was happening as part of the same agent. We realized that okay, when we don't reach consensus, we probably need to go and circle back to the other interviewers about their availability. So when we were doing the availability coordination, we realized that this is probably, if you were to do the request passing again, we are going to end up in the same problem of cost compounding, unnecessary tool calls, a lot of memory being put into the system. So this is where we realized that okay, the availability coordination needs to be another agent, and this is where we extracted it to be another agent as well. So this brings me to the next learning, which is don't build microservices again. The right size reveals itself, and as you build, you will understand what this right size for the agent is. For example, when you are building a monolithic agent, these are two cores of an agent. One agent will do a lot of things. There will be a lot of context window saturation, and there will be you may end up into following poor instructions because there's a lot of things that one agent needs to achieve. Then on the other end of the spectrum is too fine-grained control where have a lot of agents do overkill. Well, you're basically reinventing the microservices problem again. You have excessive latency costs. You have communication overhead between these agents, where multiple agents are trying to update the same state of memory, where multiple agents require different tool calls that they need to do, and they may overlap each other. So you have to find the sweet spot between these agents. You have to balance that sweet spot where these agents are rather carved out by their responsibility by balancing those five things, which is carved by memory and tools, where if you feel that an AI agent requires to be extracted out needs to have its own memory and its tools, and it needs its own reasoning loops, which is governed by the system prompt that you have. And by doing this, if it will have high reliability and focus, then go ahead and extract that as an AI agent. So how do you really, once we determined that, okay, we can build this into multiple agents, we decided that, okay, the pass and validate request is one of the agents. The check availability part where it goes and coordinates with the other interviewers is another agent. The collect availability once the interviewers have really responded back, that needs to be another agent. The evaluating consensus is another agent. Confirming availability with the recruiter and the interviewers is another agent, and this is where the system ends. Now, the way the goal of the system is still achieved is all of these agents are still autonomous in their own nature. There is no way that I can control how the output for the request passing is. I can't really control because the agent is going to be completely autonomous in choosing its path. But what I can definitely control is once I have that valid request, where does it need to go? How does it need to check availability with the others? This is where the determinism in the AI agentic workflow comes in. So the workflow is basically the spine of your system, and the agents are the reasoning for it. The way you build determinism around those agents is by making sure the workflow governs the agents, and you leave the agents free and autonomous and adaptive enough that they can make their own decisions. Now, once we had this entire workflow in place, what holds all of this agents together is what is called state. Once we have 5 agents that we have: the request parser, availability coordination, collect availability consensus, and confirmation. The only way that they can communicate with each other is by having a shared state. Now, what was the previous output of the previous agent? Where does it go? It will go in the state, and then that's where the next agent will pick that input from and then act on its own. Then would pass on the information to the collect availability. The same system would keep on repeating itself until the agent goal is reached in the agentic workflow. Now, so all of these AI agents, basically they need to share the same state. They need to be safe to resume, which means that all of the operations that they are performing need to be idempotent. The reason why they need to be idempotent is that because it can follow its complete autonomous path, you can't really say where it needs to go. It needs to be safe to resume so that you can start again the same AI agent from there. When we did all of this, we ran into another learning, which is double texting. So let's say that you have an interview schedule sent out for availability coordination, and 2 people are going to submit the availability at the same time. Now, since you cannot really control how long the agent is going to run for and what path it is going to follow, let's say another request comes in at the same time, you're going to run into a state where there's an overlap of processing by the agents and you don't really know what the shared state looks like. This is something that we faced at real time, where we tried to schedule an interview and 2 of the people click at the same time, and the workflow resumed from start. And the second interview's response could not really make it and got ourselves in a corrupted state. So once we figured out all of these learnings, we realized that it's not really about how you design these agents, but how you design beyond the happy path of running these workflows. How do you really determine the deadlocks? For example, all responded and there's not a overlap that exists. How does the AI agentic system go on looping itself until it reaches its goal? You're basically ending into incurring a lot of cost. So the system is basically stuck in an endless loop, and there's no real exit determined. So you really need to decide what your business logic, what your goal is, and how do you make sure that you build enough control around it that it needs to know how can it exit itself as well. Same is the case when you have quorum failure, when there are not enough participants that the consensus is possible in the case of scheduling an interview. Again, you're going to run into the same state of the system being stuck. So you need to design beyond the happy path of how your agentic system would reach its goal. The way we really uncovered all of these learnings was by observability. You can imagine the observability to be logging the output of what the agent did, but that was not sufficient in our case, because let's say that let's say the request parser agent goes on acting on finding the input from the request. Until it reaches its goal, it's going to go on performing the same operation in a loop. And until we have that output, we don't really have what the agent is doing. So this is where we decided to stream the agent thinking. At every step, how many number of tool calls did it make? Why did it come to that conclusion? What was the output like? All of these data we started streaming at real time so that we could make sense out of it at real time, and we could, if we were to kill an AI agent, we could basically stop it from reaching its goal in that case. The token usage was something that we started to pay close attention to, because the model can follow its own autonomous path. It may consume a lot of tokens. How do you really understand which agent is costing how much to you? How do you determine how much amount of tokens it is using? And how do you understand when do you really need to refactor this? So the way you would refactor go about doing this is that, are you putting a lot of information in context window? Are you rather putting information, should you rather put your information into a shared memory layer? All of those decisions we started uncovering when we started logging these outputs and observing them on a regular basis. Again, the tool calls, how many number of tool calls is the model doing? How many, what makes the model do so many tool calls? That's something that we realized after we had the observability in our AI agent. So yeah, with this, I think I'll probably hand it over to back to Abhijit. So this is what basically was a summary of what we learned as part of this. Yep.
Yeah, I guess the summary has been the learnings that we got is the agents are discovered, not designed. Essentially, you need to break down your agents to right granularity so that they are working at optimal cost, I would say. It's something, it's more like a design problem. As you build software systems, you come across very similar problem. The workflows governs the agent triad. I think one of the key learning was that building the deterministic part in the workflow and focusing agent to do the non-deterministic part was very, very important for us to make sure that the whole flow remains sustainable in terms of the tokens it is consuming and the speed at which it is working. And again, state is what makes it real. Essentially, understanding of what state is, what memory is used for what purpose is very key in building and setting the memory in the right way, so that you're, again, finally boils down to working more efficiently, building for resilience essentially, because these are the systems that deal with uncertainty, so they have to be very strong in terms of resilience, and that is what the memory really gives you. And finally, the control system, putting out the observability, the guardrails, the cost ceilings, the iteration limits is what ensures that you're building something that you have control on, and you don't get surprises there. That's about it. I think that's all the learnings that we had. We can have some question answers right now. Yes, please.
It seems like you've done a lot of iteration. How much time did it take you to build the entire agent?
So was that? I couldn't hear.
How much
It
time
seems
did?
like you have done a lot of iteration to get the interview assistant correct.
Yeah.
So how long did it take them?
Yeah, I think essentially we took about roughly a month or month and a half to figure out these learnings. We initially got down to creating multiple agents, like we started breaking them down. We were able to spin out the interview scheduler quickly enough, but it wouldn't really do the same operation that we were wanting to do. So example, it would start again, fine tuning it to do what it needs to do in the end. That's what took us longer to reach rather than getting an output from the interview scheduler. So that's why it's really easy to build an AI agent, but it takes a lot longer to make it do what you want it to do. Yeah.
Yes, please.
I have a question regarding shared state. So how do you coordinate shared state across the multiple agents without any conflicts?
Right. So the way we did this was that in our case, we wanted to avoid the double texting problem in the first place. In our case, we use LangGraph. LangGraph comes with its own checkpointing mechanism. So all of the what we essentially had to do was give that checkpointing mechanism to each of these agents. The agents would go ahead and update its own state. Now, we tried to avoid to reach to that state where we would have multiple agents trying to update the same state at the same time. So the way we did this was that whenever a response comes in, we enqueue that response, understand where the workflow is at. If the workflow needs to process and reach its system goal, keep continuing after the entire iteration of that AI agent goes through. Once it goes through, then queue in the next task, or either just discard it if the goal is already met.
And yeah, as he mentioned, the graph model works really well in this case. So it really helps you understand the state of your current graph, and when you suspend and resume. So it basically out of the box coming from your framework. So I would say just leverage the framework that you're using. It gives you a lot of these capabilities out of the box.
So
we'll have some. Yeah.
LangGraph and LangChain are the tech stack for this project.
Say that again.
The tech stack for this product? What is it like? Is it just
So it is LangGraph, LangChain deployed on, I think it was
So yeah,
ECS.
we deployed on containers. Basically, we built a fast API in front of it. The LangChain and LangGraph was basically for orchestrating these AI agents. The fast API would take in the responses which were webhooks from Slack, and then it would coordinate and push it to LangChain and LangGraph to do the orchestration for it. Yeah. Yes, sorry.
Yes, please.
Sorry.
Okay. Pretty quick. How are you guys measuring quantifiable results after POC? So it's deployed, right? It's working in production. How are you guys measuring the benefits, quantifying results, and etc.?
So I think at this stage, I think the key goal was to drive those insights. So in this particular use case, you're not looking at that, but I think when you go to clients, I think that is one of the first things you'll want to establish of what are your measurable success criterias that then you can actually measure before and after.
Okay. Yep.
Yes.
So I understand you used many agents, each with a different task. What was the use case that gave you the impression that you would need many agents? Because from my understanding, like if you get say an email saying, let's meet at that date, you need an agent to read that.
Yeah.
But to schedule, that can be and should be deterministic.
Correct. So in the case of not all of the agents that probably. Sorry, can you hear me? Yeah, great. So not all of the tasks that we had in the graph were AI agents trying to act with autonomy. Some of the steps, like for example, confirming the interview, was a deterministic goal which we reached at, and that was a completely deterministically implemented code that we had put in place. The part which we had initially decided, which was for negotiating interview slots, deciding on what others have accepted, and then based on that, how do I make the other interviewers accept slots which others have accepted? That was autonomous, rather than slots like other than actions like confirming availability and scheduling an interview on Google Meet. That was deterministic in our case.
Right. So basically, talking to a human at every point was conversation.
So I say that again.
So if I understood, you have many steps that use the AIs, and those steps were all conversation.
Yeah, they were conversation.
Right.
Yeah.
Thank you.
Yes, please.
Thank you.
Great case study there. I think when you get into more complex things that relate to core business in an enterprise, starting to talking about interacting with other platforms which may or may not have their own agentic capabilities. You run into trust architecture issues and concepts around state complex. What's your thinking around that, and are you seeing any emerging maturity in sort of orchestration and observability platforms that can handle that? Because if the audit trail for an agent that has to go and talk to Salesforce and SAP and your data warehouse exists in 3 separate disparate systems, that's not going to pass the test in an enterprise environment, particularly if it's high stakes and you're dealing with sensitive data.
Yeah, so I think a lot of agent frameworks are trying to sort of embrace the open standard. For example, open telemetry is something that a lot of frameworks try to adopt. So tooling is an aspect, actually, is something that you need to control. I mean, there is a lot of moving parts there as well, with MCP, for example, being used as a more common established mechanism of dealing with all the different tools in your system. So either you can bake in as part of that tooling layer that you build, bake in the observability there. But from core agent perspective, a lot of agent framework also give you that, because it is one of the building blocks, having that observability, which gives you what the agents are doing. That is more valuable. I think tooling is pretty much like you need to bake that in whatever layer you are implementing for accessing your tools. But yeah, once you get that from once you get the observability from your agentic frameworks, that also gives you almost all the information that you need. Does that answer your question? Cool.
Kind of building on from this question, after you received the logs and you observed the model and you saw what can be improved, how did you improve it? Was it as simple as just updating the prompt, or was it like a type of model that could change itself?
Yeah, I think. Hello. Yeah, probably I'll take that. So it may be as simple as updating a system prompt, but it may be also because of the kind of goal that you're trying to reach out of that agent. For example, you're trying to reach a structured output goal and you're using a model that is not capable of reaching a structured output. You're going to end up in the same problem where you would end up calling multiple tools trying to reach the same goal in a very deferred state. So it is a combination of all of that, where it is determined based on what kind of model are you using, how is your prompt structured according to that to achieve that goal, are your tools really defined well enough that the model understands them to act on them, and once those tools have been acted on, does it really maintain its state? So that's quite a measure.
Can you give an example of where you have to just change a prompt versus where you have to change your model?
Correct. So in the case of request passing wait, that was more of a structured output, where when the recruiter would send in a message saying that, okay, I would want to schedule an interview for this slot for these many people, and I would like you to find these many slots. We initially started with developing with local models like Ulama. We structured our entire prompt based on local Ulama models. Then we realized that, okay, we are not really achieving the agent goal because our agent is hallucinating itself. It was not because we had a very brief, we had a quite elaborate prompt, but it was because the model wasn't really advanced enough for it to understand what the structured output could be. When we switched to Gemini, we realized that, okay, our tooling needs to be a little bit different for the agent to discover itself, and how do I maintain that as system prompts. That's where some of the learnings came in for the request passing. Yeah.
We also get the slides.
Yeah, maybe yes. Yeah. Sure.
Cool. That's about it then. Thank you all for attending this. This is a very good turnout, so thank you all, and yeah, enjoy. There's some pizzas at the back. Important one. So
Everybody can stay back. We can do like a selfie, and Abhijit, if you don't mind doing a selfie, and people, if you can scooch in.
Yeah.
Like a group.
But they can.
yeah, but just one more important announcement. We have open roles, so we are actively hiring. We have a QR code that you can scan. We are looking at tech leads and delivery leads across India, Philippines, and China, and in Melbourne as well.
Yeah. Thank you, Abhijit and Lude. Yeah, we can just take softly, just 1 minute later. So thank you for everyone joining today's session. I'm Eva from Fabric Talent Acquisition Team, and I'm taking care of hiring talent for our organization. So I'd like to share with you that we are currently actively hiring tech lead, delivery lead in Melbourne, and also automation quality engineering and delivery lead in our offshore team based in India, Philippines, and China. So if you are exploring some new opportunities, or you know someone is seeking something new, you can scan the QR code on TV and to check more details about the job descriptions. And also, I'd like to highlight the technical lead role in Melbourne. So if you are passionate about driving technical excellence, or just you are just loving deal with some complex problems, or just leading from the front, or you are just curious about Fabric, who we are, how we work, and what we do, you can just grab me for a chat or reach out to our amazing team member, Anna, who is standing over there. So we are always up for a chat. So thank you, everyone, for joining today's session, and enjoy the night. Thank you.
Let's have a quick selfie.
Sure.
Sure.
You want to?
I'll take it.